What are matrix inverses, and how do we find them using Gauss-Jordan elimination? Well, a matrix inverse is notated like this with an A and a superscript -1. It's not raising it to the negative first power. It's just an inverse, like an inverse function, and it's the matrix such that when you perform one matrix and its inverse and multiply those together using matrix multiplication, you get the identity matrix. And also, if you perform them in the opposite order, you get the identity matrix. As a reminder, the identity matrix is this matrix with ones on the diagonal and zeros everywhere else. This is the three-dimensional identity matrix. You could also have a two-dimensional identity matrix that would look like this. You could have a four-dimensional one and just have ones, ones, one, one, and zero everywhere else. Also at the top, you should note that only square matrices have inverses. You can figure that out using the fact that using the dimensional properties of matrix multiplication, that matrices have to share the number of columns in the first matrix has to match with the number of rows in the second matrix, which means that the only way for it to work both ways, where whether you multiply A times A inverse and A inverse times A, that you get the identity, is if that both of the matrices had the same dimensions both ways. So we can only find inverse matrices of square matrices. So one way to show that two matrices are inverses is to simply multiply them together in both directions. So I'm gonna first calculate AB, and then I'm going to calculate BA, and if both of those give me inverse, if both of those give me the identity, then I'll know that they are inverses. So 3813 times 3 negative 8 negative 1 3. Well, 3 times 3 is 9. 8 times negative 1 is negative 8. 3 times negative 8 is negative 24. 8 times 3 is 24. 1 times 3 is 3. 3 times negative 1 is negative 3. 1 times negative 8 is negative 8. And 3 times 3 is 9. Simplifying each of those entries gives me 1, 0, 0, 1. So that's the identity matrix. So far, so good. Let's try it the other way. 3, negative 8, negative 1, 3. 3, 8, 1, 3. Now we're going to multiply them out. 3 times 3 is 9. Negative 8 times 1 is negative 8. 3 times 8 is 24. Negative 8 times 3 is negative 24. Negative 1 times 3 is negative 3. 3 times 1 is positive 3. Negative 1 times 8 is negative 8. 3 times 3 is positive 9. If any of this looks like magic, then go back and review your multiplying matrices. So yes, these two matrices were inverses. But how do we find matrix inverses? So one method of finding matrix inverses is Gauss-Jordan elimination. So we talked about Gauss-Jordan elimination when we were using matrices to solve systems of equations. This is the same Gauss-Jordan elimination. However, the purpose of it is different. Instead of we have an equation that can be represented by a system of equations that can be represented by matrices, now we are finding an inverse matrix using this. So the first thing is we're going to take our matrix and make it was a square matrix looking like 3, 8, 1, 3. And I'm going to take this matrix and I'm going to extend it. So now instead of it being that, it's now going to be twice as many columns, and I'm going to put the identity matrix next to it. Then we're going to perform Gaussian elimination until this matrix looks like 1, 0, 0, 1, and then there are going to be 4 entries here. And that second matrix over here should be should be the inverse matrix of the original matrix. So this is one way we can find an inverse matrix. So if we wanted to find the inverse of this using Gauss-Jordan elimination, yes, there are other methods, but 4, 3, 2, 0, and then add the identity matrix afterward. Now we're going to use Gauss-Jordan elimination. What I'd like to do is I want to rewrite this as a 1. So I'm going to divide that second row. I'm going to take row 2, divide it by 2. That's going to be 1, 0, 0, and then 1/2. Now I'm going to add -4 times that second row to the first row. So I'll do -4 times 1 plus 4 is 0. Everything else stays the same except -4 times 1/2 is going to be -2 plus the 0 is -2. Now I can switch these two rows, switch row 1 and row 2, and what we'll be left with is 1, 1, 0, 0, 1/2, 0, 3, 1, -2. We're almost in reduced row echelon form. Or, sorry, we are in reduced row echelon form, but we want this to be the identity matrix. So this is not yet the identity matrix. We need to divide the second row by 3. And when we divide the second row by 3, then we will have the identity matrix on the left. The first row stays the same. And we divided the second row by 3, so this becomes 1/3 and -2/3. So here is, here is our inverse matrix. So typically I'll rewrite it out saying the inverse of our original matrix is 0, 1/2, 1/3, -2/3. So that's how we can do this. Let's do it with a harder matrix. So here we have a 3-dimensional matrix. I'm going to extend it. And what we want to do is perform row operations on this until it becomes, until the left side is the identity matrix. So the first thing that I want to do is multiply this last row by -1/2. -1/2 times row 3, put that in row 3, because now that will be, now row 3 will be exactly what I want row 3 to look like. Yes, I'm aware that this requires a lot of writing. A common error here is to fail to multiply everything by that -1/2. So please make sure that you do so. Now it's easy to take multiples of this third row and add it to the other rows. If you don't mind me going a little faster, what I'm going to do is I'm going to add 6 times that third row to the first row, because I want that to cancel out here. I'm also going to add 3 times that third row to the second row. And yes, you can do these 2 row operations at the same time, as long as you're still not breaking any of those rules. So I'm going to do 6. So for row 1, I'm doing 6 times row 3. So most of these are staying the same. 6 times 1 plus that is 0. That's staying the same. 6 times negative 1/2 is going to be negative 3, added there. And now for the second row, I am taking 3 times row 3 and adding it there. So 5, negative 6, 0, 0, 0, and then 3 times this is negative 3/2. Now, it's really important to go back and check your work because you notice that I missed this 1 and wrote a 0 there, and that's going to mess everything up. I strongly recommend checking your work consistently throughout this process because it's easy to make small mistakes and have them snowball. Now, let's see. I'm going to multiply one of these rows by something. Let's see. Yeah, let's take the first row and divide it by negative 4. So the first row times negative 1/4. There aren't any great options of what to do here, but now we have like a system of 2 variables here, x and y. There's no z's. So if we can get this to look like a 1, then that's on our path. Negative 5/4, 0, negative 1/4, 0, and that becomes 3/4. 5, negative 6, 0, 0, 1, negative 3/2. I can't promise that this will always turn out prettily as your answer. Good handwriting does help. Take negative 5 times the first row. So this is me trying to get this to be a 0. I'm going to take negative 5 times the first row and add it to the second row. So that becomes 0. Now we will have 25/4 and negative 24/4, which becomes 1/4. This will become 5/4, 1, and negative 15/4. I'm going to need to write that down. Negative 15/4. Fourths, and then I'm subtracting 3/2, which is 6/4. So negative 21/4. 0, 0, 1, 0, 0, negative 1/2. I'm getting close. We can multiply this second row by 4. Take row 2, multiply it by 4. And now row 2 and row 3 are looking good. Zero, 1, 0, 5, 4, negative 21, 0, 0, 1, 0, 0, negative 1/2. And lastly, we can take 5/4 times the second row and add it to the first row. So 1, 0, 0. 5/4 times 5 is going to become 25/4, plus negative 1/4 becomes 24/4, or 6. 5/4 times 4 becomes 5. 5/4 times negative 21. 5/4 times negative 21. And that was 3/4 up there? Yes. Plus 3/4. So negative 105 plus 3 over 4 is negative 102. fourths, which is negative 51 halves. Negative 51 halves. And then everything else is the same. So now this is our inverse matrix.